Hello students, welcome to the structure analysis course. In the last class, we have initiated this uh, chapter that is analysis of continuous beam by three moment theory. So we have discussed about the continuous beam, what is continuous beam, what is statically determinate and indeterminate structure, what are the fundamentals of three moment theory. Then we have solved one two-span beam with point force and duty. So there is another problem also we can use by giving a uniformly distributed load in both the spans. It is similar to this. Instead of point two, there will be another UDL. So you can practice those examples. You can find some of the books and then get some examples and practice it for your exam. So today we'll discuss about how can we apply this three moment theorem in a three span beam. Okay, the beam is having three continuous beam is having three spans. So how can we apply this three moment here? So let us go into the chapter. So again, these things why three moment theorem is required to analyze a continuous beam, because to determine the support moments, we can simplify the analysis of the continuous beam and we can avoid the so many equations like simultaneous equations. Right? This is the basic equations, that is three moment theorem equations, where MA, MB, and MC are the support moments, and L1 and L2 are the span length, U1 and A2 are the area of the free bending moment diagram in the span, X1 bar and X2 bar are central distance from each support. So yeah, how we can calculate the areas. So we have to draw the free bending moment diagram. This to calculate this PAB by L1, either remember this formula, otherwise you consider this span and the including the loading diagrams and find out the support reactions and calculate the moment at this particular location where point load is there. So at the end, we can calculate PAB by L1, and area of this triangle is half into base into height. Base is L1 and height is PAB by L1. This is the height. So PAB by 2. Similarly, if there is a UDL, then area 2 will be, so first you draw the free bending moment diagram, that is WL square by 8. Area 2 will be 2/3 of the base into height. So WL square by 8. So area 2 you can calculate. So coming to the centroid will be at centroid to left support, that is your XL. XL can be calculated by using this formula A plus L1 by 3, and XR can be calculated by using this formula B plus L1 by 3. Similarly, if there is a UDL, so centroid will be at the center, that is XL, centroid to left support is XL, and centroid to right support is XR. So this is nothing but XL is L2 by 2 and XR is also same L2 by 2. So coming to the examples, let us see this warehouse loading platform. Okay, so inside this warehouse, what happens? A beam, continuous beam is there, and the beam rests on four supports A, B, C, and D. The span length are given 6 meter, AB is 6 meter, span length of BC is 6 meter, and CD is 3 meter. So during this loading operation, what happens? The beam is subjected to the following loads. What are the loads? 36 kilonewton is applied on span AB, which is situated 2 meter distance from B. Similarly, uniformly distributed load, that is 24 kilonewton per meter, Newton per meter, is applied on the span BC, and another point load, that is 48 kilonewton, is applied at the center of span CD. So this is 1.5 meter from C. Okay. So we have to assume that the beam has the constant flexural rigidity So that is why in the question it is given the I of AB, BC, and CD are same. So flexural rigidity, flexural rigidity of the beam is constant throughout. So what is the task? The task is we have to use this three moment theorem to determine the bending moments at the supports A, B, C, and D, and in this case the final bending moment diagram. I hope you understood the problem what it is asking. Yeah, as it is a three span waves, but we cannot extend this equation for the three spans at a time. So we have to write the equation for the consecutively three supports. Consecutive three supports. Support 1, support 2, and support 3. So if consecutive three supports are there, how many spans? Two spans. So at a time, you can write the equation for consecutively three supports. So if we have four supports, like three span beams, so how many equations we have to write? One equation we have to write for span A, B, C. So one equation we'll write for span A, B, and C. Another equation we'll write for span B, C, and D. So two equations we'll write while solving this example by using three moment equations. But all the procedures are similar as we have discussed in the previous class while solving a two span problems. So So let us just find out what are the free bending moment diagram of each span and what are the areas and centroid to support distance, because all these values will be required while writing the equations. So for the span AB, if you separately draw the span AB, so this end is AB, where the two simply support, and the load is 36 kilonewton, which is 2 meter from B. So for that case, just find out the reactions. What is the reaction formula? E B by L1. This is E A by L1. So moment will be P A by L1 into B. So with that, so the formula is P A B by L. So if you apply this formula PAB by L, P is 36, P is 36 into A is 4 into B is 2 divided by L or is 6. So if you solve this, you'll get 48 kilometer meter. And if you find the centroid distance, centroid to, you find the centroid distance, centroid in the F support is, what is the equation? A plus L1 divided by 3, that is XL. So XR is B plus L1 divided by 3, that is X. So area 1 will be area of the triangle. So half into base is 6 into height is 48. So we got 144. Similarly for span BC, so span BC and BC, the UDL is 24 kilonewton per meter and the span length is 6 meter. Okay. So what is the free bending moment diagram? The maximum bending moment will be WL square by 8. So here W is 24, L is 6 square divided by 8. If you use solve this, you'll get 108 kilonewton meter. And what is the distance of XL and XR? This is your XL, that is centroid to left support. This is XR, that is centroid to right support. So 3 meter and 3 meter, that is L2 by 2. So area 2 will be 2/3 into base into height. So 432 we have calculated for span BC. Similarly, we calculate for span CD also. So in span CD, the load is at the center, that is 1.5 meters from length support. So 3 meters is the total length. So what is the formula? WL by 4. So we draw the free movement diagram, and the maximum height, the maximum bending moment is W by 4. So W is here 48 into 3 divided by 4. We are getting 36 kilometer meter. In 36 kilometer meter, if you find out area 3, that is half into base into height. So you are getting 54. And what is XL and XR? So at the load is at the center. So centroid is also at the center. So XL is, that is load to left support. Centroid to left support. XR is centroid to right support. That is nothing but your L by 2, 1.5 meter. Now we'll write the equations. So if you apply the three moment equations to each span AB and BC. So at a time we will write the equation for span AB and BC. So what is the equation? As it is also given in the question that the flexural rigidity is constant throughout. So no need to write the I values. No need to write the I values in the formula. So because it will be cancelled self later. So no need to write the I values in the formula. So the formula will be MA into L1 plus 2MB into L1 plus L2 plus MC into L2 plus 6A1 X1 bar upon L1 plus 6A2 X2 bar upon L2 is equal to 0. Right? So now, if you remember what rules we have discussed in the previous class, if the end support is simply supported, so that in that case the moment at the end support will be 0. But you see in this case, as it is number of span is more than 2, so here the support A, that is end support, that is simply supported, but support C, which we are writing the equations for support C, it is not an end support. So it is an intermediate support. That means there will be some movements will be developed in the intermediate support. So MC is not 0 here. MC is not 0. So we have to only write, or we have to only consider here moment at A is equal to 0. Okay. So let us rewrite the formula again. So MA is 0, that means this first segment is 0. So the second segment, that is 2MB plus L1 plus L2 plus the third segment MC into L2 is equal to minus. So this part I have taken into right hand side. So minus 6A1 X1 bar by L1 plus 6A2 X2 by L2. So if you put the value of L1 and L2, so 2MB, L1 is 6 meter, L2 is 6 meter plus MC into L2 is 6 meter is equal to minus 6 into your A1. A1 we have calculated 144 into X1 bar, that is central to left support, that is 3.33 we have calculated by using the formula A plus L1 by 3. So again this is 6 into area 2 is 432 we have calculated into X2 bar is 3 divided by 6. So if you simplify this equation again, so 24 MB plus 6 MC is equal to minus 479.52 plus 1296. If you add both, it is minus 1775.52. So the equation, if you rewrite 24 MB plus 6 MC is equal to this. So if you simplify again, if you divide this equation by 6, so 24 by 6, that is 4 MB. So 6 by 6 is 1, so MC minus 1775 divided by 6, that is minus 296. This is your equation. This is your equation 1. Now we'll apply this equation for span BC and C2. So span B2, C and C2. So in that case, let us write the equation. So equation will be in a similar way we'll write, but the terminology will look into the moments here. The first segment, which moment will come? Moment B, that is MB into L2 plus 2MC into L2 plus L3. L2 is here. This is L2 and L3. That is the span length related to span BC and CD. Then plus MD into L3 plus 6A2 X2 bar by L2 plus 6A3 X3 bar by L3 is equal to 0. So in that case, each moment will be 0. Now see which one is intermediate support. If this B is intermediate support, so there will be some moments will be developed. C also intermediate support. The only end support is M. So MD can be 0 because if the end support is simply supported, if the end support is simply supported, then the moment at the end support will be 0. So you can consider here MD is equal to 0. Okay. So let us rewrite the formula again. So MB into L2 plus 2MC L2 plus L3 is equal to, so this part I have taken into right hand side, minus 6A1 X2 bar by X2 bar by L2 plus 6A3 X3 by L3. So rewrite it. So L2 is nothing but your 6. So 2MC, this is 6 plus L3 is 3. Total is 9 into 2, 18. So minus 6 into area 2 into x2 bar by 6 plus 6 into area 3 into x3 bar by 3. That is your L3. So if you rewrite this equation, it is 6 MB plus 18 MC is equal to minus 1296 plus 163 minus 1458. So 6 MB plus 18 MC is equal to minus 1458. So further, if you simplify this equation in terms of MC, so divide this equation by uh, 18. So it is 0.33 MB plus MC is equal to minus 81. So this is your equation 2, right? So now we have two equations. The first equation is 4MB plus MC is equal to minus 296. That is equation 1. Second equation is 0.33 MB plus MC is equal to minus 81. This is your second equation. So if you subtract this equation 2 from equation 1, so this part will be negative, this will be negative, this will be negative, will become positive. So if you subtract this, now it is coming 4 minus 0.33, that is 3.67 MB. So plus MC minus MC is cancels out, is equal to minus 296 plus 81 will be minus 215. So from here we can calculate MB. MB is nothing but minus 215 divided by 3.67. So it is minus 58.58 kilonewton meter. So now we have calculated the value of MB by solving these two equations. Now substituting the value of MB in equation 1. If you substitute the value of MB in equation 1, the 4 into, what is the equation 1? 4 MB. So 4 into minus 58.58 plus MC is equal to minus 296. So MC we are getting minus 61.68. So MC is minus 61.68. MA we have considered is 0. MD is 0. MB is minus 58.58. MC is minus 61.68. Now the part is how to sketch the bending moment diagram. If you remember in the last class I told, first we have to draw the free bending moment diagram, then a bending moment diagram, then final bending moment diagram. Okay. So here is the free movement diagram is. So this is the free movement diagram, the triangle, which value we have got. If you go to the previous slides, it is 48, 108 and 36. 48, so this value is 48, which is 108, which is 36. So this is a free bending moment diagram. What is the end moment diagram? So directly we can superimpose in the diagram also. How can you directly superimpose? Here is first you draw the free moment diagram with the triangle, then this is parabolic, then triangle. Then the free moment, what we have calculated, sorry, the end moment, it is 0. So I'm drawing it again. The end moment here it was the MA is 0. So MA is 0 and MB is 0. So here what is the MB? How much we have calculated? MB we have calculated minus 58.58. So we can draw in the upside and we can write it is negative. So 58.58 and MC we have calculated 61.60. MC is 61.61. So if you draw the point 58, 51 is 0 and only give the sign negative. Okay, so now this is your free bending moment diagram. This is your end bending moment diagram. So the final bending moment diagram, you superimpose this. So this is 48, this is 108, this is 36. Where is the point 58.58? Where is the point 61.68? So initially it was positive. So this is negative, this is positive, this is negative, and some part is here positive. And we can do the rest. Get this process, superimpose process, and this is your final bending moment diagram. This is your final bending moment diagram. I hope you understood this problem. So summary of the lecture is, so this Clapeyron's theorem, actually the three moment theorem relates to bending moment. This also we have discussed in the previous class, and three consecutive supports and then continuous beam. Why we are using this? We can determine the unknown support moments in multi-span continuous beams based on the span length, loading, and flexural rigidity. Once the support moments are found, yeah, this also I emphasized in the previous class. Once the support moments are found, we can again calculate the reactions, we can calculate the shear forces, and we can bending moment also we can calculate, and can be the shear force diagram can be drawn and bending moment diagram. Yeah, we have already drawn it, right? So this is the way we can apply the three moment theorem in three span beams. So if you have any questions, you can. So yeah. So for that, we'll solve another example, which is related to only uniformly distributed load throughout the span. Okay. So let us read this problem first. Let's say there is a continuous reinforced concrete beam used to support the roof slab of an industrial workshop. The beam rests on three supports A, B, and C, forming two spans. So now this problem is two span problems. Okay, this problem is two span problems, and it is resting on three supports. So the span AB, the length is 6 meter. Span AB length is 6 meter, and span BC length is 8 meter. The beam carries a uniformly distributed load 40 kilonewton per meter over the entire length from A to C. So the entire length from A to C, it carries a uniformly distributed load combined, which is combined weight of the roof slab, service equipment, and maintenance loads. So support A and C are simple supports, while B is an intermediate support connecting the two spans. So to ensure the beam is safely designed, so you have to, as a structural engineer, you must determine the bending moment at the intermediate support. What is the task? Task is to draw the free body diagrams and of the continuous beam showing spans and loadings. Use Clapeyron's free moment theorem determine the bending moment at the supports, calculate the support reactions A, B, and C, and sketch the qualitative bending moment diagrams of the beam. Okay, we have to assume uh, that the beam has constant flexural rigidity throughout its length. So yeah, let us solve this problem. So the equation, if you write, it's a two-span problem. So equation will be MA into L1 by I1 plus 2MB L1 by I1 plus L2 by I2 plus MC L2 by I2 plus 6A1 X1 bar by L1 I1 plus 6A2 X2 by L2 I2 is equal to 0. But in this particular problem, we have to assume the flexural rigidity is constant throughout. So no need to write or no need to consider this moment of inertia in the formula. Okay, so let us draw the free body diagram of each span. So if you consider span AB, so this is span AB, and it is loaded with a uniformly distributed load, that is 40 kilonewton per meter. The span length is 6 meter. So if you draw the free bending moment diagram, what is the maximum bending moment? WL square by 8. As we previously also we have calculated the same. So here W is 40 into L is 6, WL square by 8. If you calculate this, you will get 180 kilonewton meter. Similarly, calculate the area one first. So area one is 2/3 of base into height. So 720 is your area one, and x1 and x2. X1 is centroid to left support, or XL we can write, or x1 is L1 by 2, that is 6 by 2 3 meter. Now consider span BC. For span BC, it is again loaded with 40 kilonewton per meter throughout the span. So this is B, this is C. So the length is 8 meter. So the similar way, what is the maximum bending moment? WL square by 8. So W is here 40 into L is 8 square divided by 8. So we are getting 320 kilonewton meter. So area 2 is similarly 2/3 into base into height, and x2 is nothing but your L2 by 2, that is 4 meter. So apply the equation, three moment equation. If you apply for the span A, B, and C, so the final formula is MA into L1 plus 2MB into L1 plus L2 plus MC into L2 plus 6A1 X1 bar by L1 plus 6A2 X2 bar by L2 is equal to 0. So as the both end supports are simply supported, so we can consider MA and MC is equal to 0. We can consider MA and MC is equal to 0. So if you rewrite the equations, so MA part is 0, MC part is 0. So the final equation is 2MB L1 plus L2 minus 6A1 X1 bar by L1 plus 6A2 X2 bar by L2. So 2MB, what is the L1 value? 6. L2 is 8 minus 2 minus 6 into 720 is your area 1 into x1 is 3 divided by 6. And same here, the 6 into area 2 is 1706.67 into 4 by 8. So the final equation is 28 AMB is equal to minus 7280. So from this equation, we can calculate what is MB. MB is minus 260 kilonewton meter. We can calculate the MB from the equations. Now the bending moment diagram. So how to draw the bending moment diagram? First draw the free moment diagram as I told. Free moment diagram, this value is WL square by 8, that is 180. This is 320. So we have to superimpose the free moment diagram. What is the end moment diagram? What are the end moment diagram we have got? This is 0, this is 0, and this is we got MB, that is minus 260. We can directly write minus 260, or we can write 260. Here we can give negative sign. So how to draw the final bending moment diagram? The final bending moment diagram is first draw the free moment diagram, then we superimpose this. If you superimpose this, this is 180, this is 320, this is 260, that is negative. So this part is, the common part is positive, which is negative, and this part is positive. This is your final bending moment diagram. I hope you understood this problem. So here is a it is not the right example. Here the UDL is there. So summary, yeah, we have already discussed this. So what is the purpose of this three movement theorem? What is the use of it? What happens in the two simply supported spans if UDL end support moments are zero, and the theorem is to find the moment at the middle support. So it helps to determine the moment distributions and reactions in the continuous field efficiently. I hope this three moment theorem is clear. Okay. So thank you. If any questions, we can discuss. Otherwise, we'll be end this.